This video is going to cover matrix multiplication. In this video, we'll first review matrix addition, review scalar multiplication, review finding the inverse, which we know entails finding the determinant and the adjoint, and then we'll introduce matrix multiplication. By the end of this video, you should understand that matrix multiplication is not commutative, but it is associative. And you'll also know that a matrix multiplied by its inverse gives you the identity matrix. Finally, you should be able to use matrix multiplication to solve simultaneous equations. And we'll do a couple of CSEC questions at the end just for practice. So let's review matrix addition first. Remember, when we're adding matrices, you can only add matrices that are of the same order. That means they have the same number of rows and the same number of columns. So before you do any calculation with matrices, you want to check the orders of the matrices. So they're asking you to add this matrix and this matrix. First, we're going to check their orders. Remember, order is row times column. So you're going to see how many rows are horizontal, so how many rows of numbers. So in this case, we have 2 rows of numbers. And you're going to see how many columns, like columns that you build houses on. If you do a column, this is a column. This is 2 columns. So this is called a 2 by 2 matrix because it has 2 rows and 2 columns. This matrix has 2 rows, and if you see how many columns you can build here, 1, 2, 3 columns. It's 2 by 3. So you can only add matrices that are of the same order. These are 2 different orders. This is a 2 by 2 and this is a 2 by 3. So this addition is not possible. We need to add these matrices, however, if we check the orders. Remember, we always check the orders first. This has 2 rows, and we build columns. You got 2 columns. And this matrix has 2 rows, and if we build some columns, 2 columns. These have identical orders. That means you can add them. So this is possible. Now, once you find 2 matrices that have the same order, that means they can be added, and the answer matrix will also have the same order. So if I add this matrix and this matrix, I know that the answer will also be a 2 by 2 matrix. So these have 4 digits in them, 4 elements. This will end up having the same 4 elements. And when we're adding, it's very simple. You just add the corresponding elements. So this 3 is at this top spot, and this 1 is also at the top spot, so it's 3 plus 1 in that spot. In this spot we have 5 plus -7. In this spot you have 2 plus -3, and in this spot you got 4 plus 8. If you solve these, you can use your calculator, or you can just solve them. 3 plus 1 is 4. 5 plus -7. If you have 2 signs together, we know it'll be a negative. The negative wins. 5 minus 7, we got -2. Here, we have 2 signs together again, so that's negative. 2 minus 3, that's -1. 4 plus 8, 12. And that's our answer. So why did we have to review addition in a multiplication video? That's because addition and multiplication are related. Multiplication is just repeated addition. Okay? So when we go on to multiplication, we'll see that multiplication is just repeated addition. Scalar multiplication. First of all, what is a scalar? A scalar is just a number, or sometimes they put it as a fraction, but the point is a scalar is not a matrix. It's not something in square brackets with several different elements. It's one element altogether. It's just a number or just a fraction. We're multiplying a matrix by a scalar, so we're multiplying a matrix by a regular number. To multiply a matrix by a scalar, you just multiply each element in the matrix by the scalar. So if you have 2a, so a is 5, negative 2, 3, 7. If we have to do 2 times a, this is the scalar 2, it's just a regular number, 2 times a. So it's 2 times a, which a is 5, negative 2, 3, 7. That means the answer is you're just going to multiply 2 by every single element. So you're going to do 2 times the 5 in that spot, 2 times the negative 2 in that spot, 2 times 3 in that spot, 2 times 7 in this spot. So the answer is 10, negative 4, 6, 14. So that's scalar multiplication. You just multiply each thing inside the matrix by the scalar. Now, if you can't remember how to multiply using scalar multiplication, you can remember that multiplication is just repeated addition. Repeat addition, that's multiplication. What do I mean? 2 times a. 2 multiplied by a just means we're adding a 2 times. So if we do a, 5, negative 2, 3, 7, so that's 1a plus another a, that makes 2 a's. Then you'll get, if you do your additions, you just add everything, and we'll see that we get the same answer, 10, negative 4, 6, 14, because it's the same thing. Multiplying is the same thing as adding. So 3a would be 3 times a. If we do it using scalar multiplication, then we just multiply each thing inside the matrix by the scalar. 3 times 5, 3 times negative 2, 3 times 3, and 3 times 7, you'll get 15, 9, negative 6, and 21. If you cannot remember scalar multiplication, then you just remember that repeated addition is multiplication. So instead of doing 3 times a, I could do a plus another a. So here we already had a plus a, gave us this. So we just need to plus another a, and we should see that we should get the same answer as 3 a's, because we did 1a plus another a gave us this, and then we're adding a third a. So we should get the same answer. We do 10 plus 5, that's 15. Negative 4 plus negative 2 is negative 6. 6 plus 3, that's 9. 14 plus 7 is 21. Same answer. So we're just remembering that multiplication and addition are related. Now, what if the scalar that they gave you is a fraction? If the scalar is a fraction, you just follow the same steps. You're going to be multiplying each element inside the matrix by the scalar. So, one, I guess you could say, shortcut is once the numerator is 1 of that fraction, you can just put everything in the matrix over that denominator. So if we do 1/5 times 5, then you're basically just putting the 5 over the same denominator. If we do 1/5 times negative 2, same thing. Negative 2, you just put it over the denominator. 3 and 7. Just put them all over the same denominator. Yes, and we'll simplify the easy one to simplify, which is 5 over 5 is 1. So our answer is 1. This is negative 2 over 5, 3 over 5, and 7 over 5. So to multiply fraction scalars, you just multiply them the same way. And if the numerator is 1, you just put each element over that same denominator. Before we get into matrix multiplication, we have one more thing to review, and that is finding the inverse of a matrix. To find the inverse of a matrix, there are 2 ingredients you need. You need to find the adjoint and the determinant. Then you can find the inverse of the matrix. An inverse of a matrix, which has the symbol to the power of negative 1. To find that inverse, you need to do 1 over the determinant times another matrix, a new matrix called the adjoint. So before you can use this formula, before you can do scalar multiplication of a fraction here, 1 over the determinant times the adjoint, you need to find the determinant first to put in the denominator and find the adjoint. We have a matrix here, 9, 5, 3, 2. This matrix A, and they're asking us to find the inverse of A. Find A to the power of -1, which is the inverse of A. And so to find the inverse of a matrix, you have 3 things you have to do. Find the determinant, find the adjoint, and then you can finally find the inverse. Now, determinant. First of all, determinant has 2 different symbols. You can say DET and the matrix, so determinant of A, or you put 2 vertical lines and you put A in the middle. This is also a symbol for determinant of A. What is the determinant? If you have a matrix A, B, C, D, then its determinant is going to be equal to the leading diagonal, so this diagonal here, so A times D minus the other diagonal. So you do AD minus BC, and that will give you the determinant. AD minus BC, that gives you the determinant. So let's find our determinant of A. A is 9, 5, 3, 2. To find the determinant, we know determinant is AD minus BC. That's our determinant. And AD is the leading diagonal. So for our A, here's our leading diagonal here. That's 9 and 2. So we know it's AD minus BC. So it's 9 times 2, that's AD, minus the other diagonal, which is 3 and a 5. And the answer to this should be our determinant. So AD minus BC, 9 times 2 is 18, minus 3 times 5 is 15. Our determinant is 3. Determinant of A is 3. When we do our leading diagonal, so 9 times 2, take away our other diagonal, we get 3. So that's the first ingredient. We found the determinant. Next, we need to find the adjoint. Now, adjoint is a matrix, as we see here. An adjoint is a matrix. So how do we make this new matrix? So the adjoint, if we have a matrix B, A, B, C, D, the adjoint of it would be the A and the D swap places and become DA, and B and C, they stay in their place, but they change their signs. So it becomes negative B and negative C, and that's the adjoint. So you swap the leading diagonal and you change the signs of the other diagonal. So if we have to find the adjoint of A, this is the regular A. The adjoint of A means I have to swap my leading diagonal, 9 and 2, so they're going to switch places, so 2 will go here instead, and 9 will go here, and the other diagonal is going to just change signs. So I have a 5 and a 3. This 5 is positive, so now it's going to become negative, and this 3 is positive, so now it's going to become negative, and I found the adjoint. So I found the second ingredient. All I had to do was switch the 9 and the 2 and change the signs of the 5 and the 3. Finally, now that we have the 2 ingredients, the determinant is 3 and the adjoint is 2, -5, -3, 9, we can find the inverse. The inverse of a matrix is 1 over the determinant times the adjoint. Our determinant is 3. To find the inverse of A, we have to do 1 over 3, because that's 1 over the determinant, times our adjoint, which is 2, 9, because those swap places, and -5 and -3, because those change the sign. Now we're just doing scalar multiplication, because this is a scalar, even though it's a fraction, and we're just multiplying by each thing. Remember, if the numerator is 1, all we have to just put the denominator on each element in the matrix. So we end up with 2 over 3, -5 over 3, -3 over 3, and 9 over 3. And then we'll simplify the ones that are easy to simplify. So 2 over 3 can stay, -5 over 3 can stay, Negative 3 over 3, that's 2 3s, so that can just become 1, so it's negative 1. And you can check all of these in your calculator. 9 over 3 is 3. And this is our inverse of our matrix. If a matrix has a determinant of 0, it is called a singular matrix. And that means it has no inverse because you can't divide by 0. And to find the inverse of a matrix, we did 1 over the determinant. So if the determinant is 0, you can't do 1 over 0 because you can't divide by 0. So they will have no inverse. And it will be called a singular matrix. So for example, C here is a singular matrix. That means if I try to find the determinant of C, it should actually be 0 if it's a singular matrix. So let's check how you find the determinant. Remember, determinant is equal to AD minus BC. That's our leading diagonal minus our other diagonal. So our determinant of C is going to be our leading diagonal here. That's 3 times 4 minus our other diagonal, which is 6 times 2. 3 times 4 is 12. 6 times 2 is 12. 12 take away 12 is 0. So this is a singular matrix, which means it has no inverse. Or you could say it means the determinant equals 0. Why do we call these matrices that don't have inverses singular? We call it singular because it does not have an inverse. And an inverse is actually a partner who you can multiply with to become one. Just like in the Bible, you know. When two people get married, they become one and they be fruitful and multiply. Well, it's the same thing with matrices. If a matrix multiplies with its inverse, it becomes 1. In the matrix world, 1 is the identity matrix. And it looks like this. Instead of just writing a number 1, to write number 1 in matrix form, you just put a leading diagonal with 1s and everything else is 0s. So if you want a 2 by 2 matrix, then you do a leading diagonal with 2 1s and all the rest 0s. If you're doing a 3 by 3 matrix, you have a leading diagonal with 1s, all the rest 0s. So identity matrix I is just 1 in matrix format, and this is how it looks. A matrix times its inverse should give you 1. They should multiply to become 1. A singular matrix doesn't have an inverse, so it can't multiply with anybody. So it's singular because it has a determinant of 0. It has no inverse. It can't ever multiply with something to become 1. Now that we're done reviewing all of the things we have to review, we can get straight into the actual topic of this video, which is matrix multiplication. Now, before you multiply a matrix by another matrix, you have to check if the two matrices are conformable for multiplication. That means, is matrix multiplication possible? So how do we check if it's possible, if the two matrices are conformable for multiplication? The first step is to line them up correctly in the correct order given. In this situation here, we have a matrix L, which is 9, 5, 3, 2, and we have a matrix M, which is 2, negative 4. And the question says, find the matrix product, product means multiply, find the matrix product LM, that's A. B says, find the matrix product ML. The order of the matrices matters. So the first thing you have to do is to line them up correctly in the correct order given. So LM means I have to put L first, then M. So L first, and then M. And for part B, it was asking me for ML, so I would have to put M first and L second. So you line them up in the correct order. You have to line them up in the correct order because matrix multiplication is not commutative. Multiplying A times B is not the same, not equal to multiplying B times A. So it's not commutative. The A cannot commute, like walk over here and become BA, and it's the same thing. It's not the same thing, so it's not commutative. So LM should not be the same thing as ML. before we can even check if that is so, we have to see, is the multiplication even possible, by writing the orders of the matrices. Our first matrix over here, we do rows times columns. So 2 rows and how many columns? That's 2. And this matrix has how many going across? That's 2. And how many columns? That's 1. Write the order. So to everything there is order. You have to write them in the correct order and then still write their actual orders underneath. If the inside numbers match, when I say inside numbers, if these two numbers on the inside match, then that means the matrix multiplication is possible. So these two match, so that means this is possible. However, let's do the orders of these matrices over here. So that has 2 and 1 column, and this one has 1, 2, and 1, 2 columns. If we look at our inside numbers, we see they do not match. This has a 1, this has a 2. They do not match. That means matrix multiplication is not possible. So if we had a question like this and we checked, we could just say, not possible. Can't even multiply. This one is possible. So we can keep moving forward. Now, there's one more step. For those of us who love to recycle, all my green people, these numbers do not go to waste, these numbers on the outside. Lucky for you is that we can use them. They are important. They do tell us something. So these outside numbers, smile, these outside numbers actually tell us the order of the answer matrix. So if I multiply L times M, I know these inside numbers tell me, yes, I can multiply L times M. And these outside numbers tell me the answer to this multiplication is going to be a 2 by 1 matrix. That means the answer to this multiplication will have 2 rows and only 1 column. Yes? So we'll just have something here and something here. These outside numbers tell you the order of the answer matrix. Let's actually get into doing the matrix multiplication. So we have our LM, our same LM from the last time, and we need to find the matrix product. So first of all, we need to put them in the correct order. So we're trying to find LM, so we have to put L first, then M. If we had to check if it was possible, we said this is 2 rows and 2 columns, and this is 2 rows and 1 column. The inside numbers match. That means yes, these two matrices are conformable for multiplication. It can happen, and we're not going to let anything go to waste. So these outside numbers tell us our answer to this multiplication will be a 2 by 1 matrix, meaning you're going to have 2 rows and it will be 1 column. Now, to multiply a matrix by another matrix, you multiply the rows of the first matrix by the columns of the second matrix. That means I'm looking at the row of the first matrix. So my first row in my first matrix is also going to give me the answer for my first row. First row gives you the answers for the first row. For the first row, I'm going to have 9 and 5. And they're going to be being multiplied by the column of the second matrix. So we're going to be multiplying that first row, that 9 and that 5 in that first row, by the first column of the second matrix. So that's 2 and 4 in that order. 2 and -4 to be exact. Now you're going to put these in brackets, and what you're going to be doing is adding them, because remember, multiplication and addition are related. At the top here, we know for our first element at the top, we're using our first row, so it's 9 and 5, and it's being multiplied by the first column, which is 2 and -4, and you will be adding everything together. And then second row, so we're looking at the second row, which is 3 and 2. and it's being multiplied by the column. We did first row and first column. Now we're doing second row, still same column. Second row, first column. So we have 3 and 2, and that's going to be times 2 and negative 4. We put those in brackets and we're adding them. So now we got 9 times 2 is 18 plus negative 20, and 6 plus negative 8, which is, we have 2 signs coming together, so we know it's minus. 2 different signs coming together, so it's minus. 18 minus 20 is negative 2, and 6 minus 8, also negative 2. So the matrix product LM ended up equaling to negative 2, negative 2. Okay, so now that we know how to multiply, or we at least know the basics, how to multiply, let's confirm this theory that A times its inverse should give us the identity matrix. So we have A is 9, 5, 3, 2, which we already found the inverse of this when we were reviewing finding the inverse. So when we were reviewing finding the inverse, we had A was 9, 5, 3, 2, and we found the determinant. We did AD minus BC, and we got 3. We found the adjoint by swapping the 2 and the 9 and changing the signs of the 5 and the 3, and then we put it all together. We did 1 over the determinant times the adjoint, and we got the inverse of A. This is the inverse of A right here, so let's just copy it over so we don't have to calculate that again. So our inverse of A was 2 over 3, negative 5 over 3, negative 1, and 3. So now we're checking if it is true that A times its inverse will give us the identity matrix. So let's line them up, and we're going to put the orders of the matrices first. So we have 1, 2 rows, and 1, 2 columns. And for the inverse, we have 1, 2 rows, and we have 1, 2 columns. The inside numbers match, so that tells us yes, we can do this multiplication. These matrices are conformable for multiplication, and these outside numbers will not go to waste. We will recycle, and it will tell us how the answer matrix is going to look. It's going to be a 2 by 2 matrix. So that means the answer matrix will have 2 rows and 2 columns. So that means it's really looking like it has something in this, something in there, something in here, something in here, right? So that means I have 1, 2, 3, 4 things inside of my matrix. Yes? It's a 2 by 2 matrix. It has 4 things in there. Now, how are we actually doing this multiplication? You're doing rows of the first one times columns. So this first element here is in the first row and it's in the first column. So we're doing the first row, that's 9 and 5, and it's in the first column. See, this is the first column here. So the first column, so this first row times this first column. So it's going to be times 2 over 3 and times negative 1. And that's going to be an addition situation. Now let's do this. Let's just keep on the same row. Let's finish with the row. So we're doing this same top row, but we're doing the second column. So we're doing still first row and we're in the second column. So first row, we got 9 and 5. And this time we're doing this times the second column because this is in the second column. So negative 5 over 3 and 3. Put these in brackets and we're adding. Yes. Now we're going down to the second row. So now we're going to be using the second row. So this is the second row and first column. So second row, that's 3 and 2. And we're doing the first column. So that's times 2 over 3 and times negative 1. We put these in brackets and we're adding. And then over here, we're doing second row. So that's 3 and 2. And we're multiplying this time. We're doing the second column. So that's -5 over 3 and 3. And we're adding them. So on my first row, I should have the numbers that are in the first row of the first matrix. So that's 9 and 5. So on my first row, I should have first row things, 9 and 5. Yes. And on my second row, I should have second row things, which are 3 and 2 and 2. Now in my first column, I should have first column things. So that's going to be 2/3 and -1. And in my first column, I should have first column things. So that should be 2/3 and -1. So in that first column, I should see same, and those same things should be from the first column. And in my second column, I should have second column things. So -5 over 3 and 3 and -5 over 3 and 3. Now all of these multiplications, they should go in their brackets and you're adding. Remember, multiplication and addition, related. So now let's find our final answers. So let's put this in the calculator. So we have, let's do this first element. So in the first element, you have 9 times 2 over 3, close brackets, plus 5 times -1. That is 1. So that first one ended up being 1. Let's do this next one. We got in the brackets 9 times -5 over 3, close brackets, plus 5 times 3. We got 0. Next one. Down here we're doing 3 times 2 over 3 plus 2 times -1. That's 0. And last element, 3 times -5 over 3 plus 2 times 3. Do not forget to add, and it's 1. And we'll see here that we did in fact get the identity matrix. So we multiplied A times its inverse, and we ended up with the identity matrix. That's what happened. Before we move on to simultaneous equations, let's just try and apply everything we've learned so far by doing some past paper questions. So these are questions from CSEC exam papers. The first one, calculate the matrix product. So product already tells us we're multiplying. AB, where A is the matrix 1, 1, 2, 3, and B is the matrix 1, 2, 0, 1. So the first thing you're going to do is line them up exactly as they told you to, in that order. So it's A, B, so we're going to put A first, next to B. We're going to write their orders. So we have 2 rows times how many columns. I'm not putting the columns on the first one because when we're doing the actual multiplication, you're doing the rows of this one times the columns of this one. So times the columns is going to be 2 columns. And the order of this matrix, we have 2 rows and 1, 2 columns. The inside numbers are the same, so these are conformable for multiplication. And the answer matrix will be a 2 by 2 matrix. So we know it's going to be equal to a 2 by 2 matrix. So we're doing on the first row. So on the first row, it will have first row things. So on the first row, we have 1, 1, 1, 1. That's on the first row. And the second row will have second row things. That's 2, 3, and 2, 3. Now the first column, here's the first column. It will have first column things. That is 1 and 0. That is 1 and 0. And we know they're going to go in brackets. And we're going to add them. The second column needs second column things, which is a 2 and a 1, 2 and a 1. And they're going to go in brackets. And we're going to add them. Now we do this in our calculators, or we can just do it by hand. So 1 times 1 is 1, plus 1 times 0 is 0. And here we have 1 times 2 is 2, plus 1 times 1 is 1. Here we have 2 times 1 is 2, plus 3 times 0, which is 0. And 2 times 2 is 4, plus 3 times 1, which is 3. So finally, AB is going to be equal to 1, 3, 2, 7. There's your answer. Now, next, show that the matrix product of A and B is not commutative. That is, AB is not equal to BA. How can we show this? So we've already found AB in part 1. So if we find BA and they're not equal to each other, then we know A and B not commutative. AB is not the same thing as BA. So we already know AB. So let's write AB. AB is what we found in the first question. Now let's find BA and see if they're the same. So before we can find it, we have to line them up in that order. So B first this time, 1, 2, 0, 1, and A second this time, 1, 1, 2, 3. We already know their orders. They're both 2 by 2s. So that means yes, this is possible. And our answer matrix will be a 2 by 2. So, boom, that's 4 things. Now, remember you're doing the rows of the first one by the columns of the second one. So let's do the rows. So on my first row, I should have 1 and 2. On my first row, I should have 1 and 2. On my second row down here, I should have 0 and 1, 0 and 1. On my first column, I should have 1 and 2. So 1 and 2. First column, 1 and 2. And we know these are going in brackets. Yes. And in my second column, I have 1 and 3. 1 and 3. And we're adding them. Make sure to use the brackets when you put it in your calculator. So now we're going to do this. We got 1 times 1 is 1, plus 2 times 2 is 4. On this line we have 0 times 1 is 0, plus 1 times 2 is 2. And on this line we have 1 times 1 is 1, plus 2 times 3, which is 6. 0 times 1 is 1, plus 1 times 3, which is 3. Your final answer is 5, 7, 2, 4. So when we did BA this time, we got BA as 5, 7, 2, 4. These are not equal to each other. So we have shown that matrix multiplication is not commutative. AB is not the same as BA. You do have to do it in the exact order that they gave it to you, because you will not get the same answer. Next part of the question. Find a to the power of -1. That means the inverse of A. So A was 1, 1, 2, 3. And we need to find its inverse now. What's the formula for the inverse of a matrix? It is 1 over the determinant of the matrix times the adjoint of the matrix. Remember, there's 2 ingredients. We have to find the determinant, then the adjoint, and then we have a third step, which is to actually find the inverse. So let's do the first step. Let's find the determinant. So determinant, what's the formula for determinant? AD minus BC. That is the leading diagonal. So 1 times 3 minus the other diagonal, which is 2 times 1. So determinant is 3 minus 2, which is 1. So we found the first part of the inverse. The next thing we have to do is the adjoint. And if we remember, for adjoint now, you swap. So for the adjoint, if you have A, B, C, D, what you're going to do is swap A and D. So it becomes D, A, and just change the signs of B and C. So our A is 1, 1, 2, 3. That means our adjoint, we swap the leading diagonal, so the 3 will go here and the 1 goes here. And we change the signs of the 1 and the 2. They're both positive, so they'll become negative. And we found the second piece of the puzzle. Now we can put it all together now. Our A inverse is going to be equal to 1 over the determinant, which was 1. So that's just 1 over 1 times the adjoint, which is 3, negative 1, negative 2, 1. And 1 over 1 is just 1. So that's just 1 times 3, negative 2, negative 1, 1. And you just multiply each thing inside the brackets, inside the matrix, by the scalar. So 1 times 3 is 3. 1 times negative 1 is negative 1. 1 times negative 2 is negative 2. 1 times 1 is 1. And this is our inverse. The last part for this question, given that m equals 2x 293, calculate the values of x for which this symbol also means determinant. The determinant of m is 0. So, how are we going to do this? They're saying the determinant of m is 0. So, how do we find determinant? We know that determinant is AD minus BC. So, determinant of m, our determinant of m would be leading diagonal, so 2x times 3 minus 2 times 9. So that would be 2x times 3 would be 6x. You just do the numbers by each other. 3 times 2 is 6. Keep the letter. And minus 2 times 9, which is 18. Now they also told us that the determinant of m equals 0. So that means this determinant equals 0. So they're saying 6x minus 18 equals 0. Now you can solve. So before we couldn't solve this. These can't combine because they don't have the same letters. But now we can combine it because we know what it's equal to, which is 0. So we just do some algebra. This goes over here, becomes plus 18 because it went over the equal sign. So now we have 6x equals 0 plus 18. That means 6x equals 18. 0 plus 18 is 18. How we get rid of the 6 that's attached to the x? We divide so that they can cancel out. Whatever you do on one side, you have to do on the other side. So x is equal to 18 divided by 6, which is 3. So you've solved for x. So if you get a question like this, and they say that the determinant is this, they mean They want to see you use the formula first and then set it equal to 0 and you solve. And if a determinant is 0, we know that this is a singular matrix because it has a determinant of 0. That means it has no inverse. The next question from CSEC says, matrices A and B are such that A is equal to 3, 2, 5, 4, and B is equal to 4, 0, 3, negative 1. Show by multiplying A and B that AB is not equal to BA. So again, they're giving us a problem here where you have to show that matrix multiplication is not commutative. Right? How can you show this? You can just do AB, do BA, and you show that they do not equal to each other. Right? So if we do AB, that means we're putting A first and B second, and we're going to multiply them to see what the answer is. Then we'll do BA over here. In this one, we'll put B first and then A, and we'll multiply those to see what BA is, and we'll see that they're not equal to each other. So how do we multiply matrices? We're doing the rows of the first one by the columns of the second one. Rows of the first one by the columns of the second one. So first row has 3, 2. So on the first row, I should see 3, 2. On the second row, I should see all 5 4s. 5, 4. And on my first column, each one should have 4, 3. 4, 3. 4, 3. And we know this is multiplication. And we put an addition in the middle. In my second column, everybody should have a 0 and a negative 1. So this should have a 0 and a negative 1. And this should have a 0 and a negative 1. And we're multiplying. And it's addition in the middle. So we got over here, we have 12 plus 6, 20 plus 12, 0 plus negative 2, and 0 plus negative 4. Final answers, 18, 32, negative 2, negative 4. This is AB. Now let's do BA and see if we get the same 18, 32, negative 2, and negative 4. So on our first row, we should have 4, 0, 4, 0. And on my second row, I should have 3, negative 1, 3, negative 1. On my first column, each element in that column should have 3 and 5. So this element here should have 3 and 5. And this element that's also in that first column should have 3 and 5. And we know it's multiplying. And we put an addition between them. And over here is my second column. So that means each element should have 2, 4. 2, 4, 2, 4. And we're multiplying. And then we can do, that's 12 plus 0, 9 plus negative 5, 8 plus 0, 6 plus negative 4. And we're going into the other question. So let's just put the answer over here. So we got 12, 8, 4, because that would become minus. 9 minus 5 is 4. And this would become minus. 6 minus 4 is 2. And that would be BA. And we can see off the bat they are not equal to each other. So these are not equal. So you've shown that. Next one. Find the inverse of A. Find A negative 1, or the inverse of A. So what's A? A is 3, 2, 5, 4. The inverse is 1 over the determinant times the adjoint. So we need to find determinant. We know determinant is AD minus BC. So in this case, that's 3 times 4 minus 2 times 5. We got 12 minus 10. That's 2. So we found our determinant. That's ingredient number 1. Now we have to find our adjoint, which we know is, you swap the A and D and change the signs of the other diagonal. So this diagonal will swap, 4 and 3. These will just change signs. They're positive, so they'll become negative. And we found the adjoint. That's our second ingredient. So now we can find the actual inverse. So the inverse is 1 over the determinant, so 1 over 2 times 4, negative 2, negative 5, 3. That's the adjoint. And how do we do scalar multiplication with a fraction that has a numerator of 1? Is we just put the denominator on everybody in the fraction. So it's going to become the 4 over 2, the negative 2 over 2, the negative 5 over 2, and the 3 over 2. And you can simplify the ones that are easy to simplify. Like we know 4 over 2 is 2, and we know negative 2 over 2 is negative 1. The others can stay as they are. And this is our A inverse. The next question says, write down the 2 by 2 matrix representing the matrix product of A times its inverse. And we don't even have to calculate A times its inverse because we already know A times its inverse gives you the identity matrix. If you didn't know, then you could have calculated it. You could just multiply A by the inverse that you just found and you would get I, but we know it, and we know it's a 2 by 2 matrix I. So it said to write down the actual matrix. So I is going to be, we know that 1s will be the diagonal and everything else would be 0. Because the identity matrix is just 1 in matrix form. Next question. Remember, as we're doing the questions, feel free to pause the video and try it by yourself first and then watch it to see if you got it correct. Well done. And if you didn't get it correct, where did you go wrong? How can you make sure you don't make the same mistake the next time? So, next question. Calculate the matrix product of 5, 4, negative 3, negative 2 times 2, 1, negative 4, 0, 3, 6. First thing we're going to do is check if it's possible. So we're doing rows. That's 2. And how many columns? That's 2. This one has rows. That's 2. And how many columns? 1, 2, 3 columns. Now, is it possible? You look at the inside numbers and they match. So yes, these two matrices are conformable. This is possible. And we don't waste anything. These on the outside tell us the order of the answer matrix. So how is the answer matrix going to look? It's going to be a 2 by 3 matrix, just like this one. So we know this time it's going to have something here, something here, something here, something here, something here, something here. That's how it's going to look. Now let's make a bigger answer matrix because we know our matrix multiplication workings are quite long. So let's go. That means we need a longer line, longer line, longer line. It's going to be a 3-part, a 2 by 3 matrix. So that's how we're going to write our answers. Now on our first row, we know we're using our first row. So everybody on the first row should have 5, 4. So 5, 4 on the first row. And everybody on the second row should have -3, -2. Every single one. Now let's deal with our first column. First column should have 2, 0. Everybody in the first column should have 2, 0. 2, 0, 2, 0. And we know it's multiplying. And we're adding in the middle. Now second column. Everybody in the second column should have 1, 3. So 1, 3, 1, 3. And everybody in the third column should have -4, 6. -4, 6. -4, 6. And now we can do the actual working. Let's just use our calculators this time. So we're gonna do 5 times 2 plus 4 times 0. First answer we got 10. Let's just prepare the matrix. All right, let's do this one at the top middle. 5 times 1 plus 4 times 3, 17. Now we're doing the second row. We got -3 times 2 plus -2 times 0. We got -6. Next one, -3 times 1 plus -2 times 3. I'm not saying the brackets, but make sure you're putting the brackets in the calculator. So bracket -3 times -4 plus brackets again, -2 times 6, close bracket, 0. And that is our matrix product. If you want to write it nicer without the lines, we have 10, 17, 4, -6, -9, 0. Now, state why the two matrices in AI are conformable for multiplication. That means, why is it possible? And we know why it's possible. It's because these two digits match. But how are we going to write that in words? We're going to say, we know the order is rows times columns, right? This is rows times columns. So we're going to say that because the first matrix has the same number of columns as the number of rows in the second matrix, that's why they're conformable. So these are conformable for multiplication because the first matrix has the same number of columns as the number of rows of the second matrix, right? If that sounds too complicated, you could say the first matrix has 2 columns and the second matrix has 2 rows. These are equal. something like that. Something to show that you know, because these two numbers in here are equal, that's why they can multiply by each other. Now, the second part of this question, part B, says, determine the inverse of 5, 4, negative 3, negative 2. And we know that inverse is 1 over determinant times adjoint. So first we need to find determinant and adjoint. Determinant is AD minus BC, so that's the leading diagonal, minus other diagonal, that's negative 10 minus negative 12. This time we have two of the same signs coming together, so it actually would become plus. So it's negative 10 plus 12, which will give us 2. So our determinant is 2. And our adjoint, how do you find the adjoint? You swap the leading diagonal. So the negative 2 will go at the top this time, and the 5 go here, these swap places. And the other diagonal just changes the sign. So it's still a 4 here, but this was positive, so now it's negative. And it's still a 3 here, but it was negative, so now it's positive. And this is the adjoint. Now we can put this all together. We'll get 1 over our determinant, so 1 over 2, times our adjoint, which was negative 2, negative 4, 3, 5. How do we do scalar multiplication with the fraction? We just put the same denominator on everybody in the matrix. So that's going to be negative 2 over 2, 3 over 2, negative 4 over 2, and 5 over 2. This is our inverse. We can simplify the easy ones to simplify. So we can say it is negative 1, negative 2, and we keep these ones the same. And this is our inverse. One more past paper question before we move on to using the matrix multiplication to solve simultaneous equations. Now, the 2 by 2 matrix C is defined in terms of a scalar constant K by C equals 3K64. Determine the value of K given that the matrix C is singular. So what does that mean? So we're trying to find K, we know that. But they told us that the matrix C is singular. That means the determinant is equal to 0. So if we find the determinant, then we can set it equal to 0, and we can just do algebra to find K. So let's find the determinant of C. Determinant is AD minus BC. So leading diagonal, that's 3 and 4. Take away other diagonal, which is 6 and K. 3 times 4 is 12 minus 6K. And they told us it's singular, so we know that the determinant is equal to 0. So we can now set this up to where we got, since there's a letter in there, equal to 0. So if 12 minus 6K, the determinant, is equal to 0, how can we solve now for K? So we're solving for K, so we're getting rid of the number that's far away from it, so we're carrying that over there. It's positive over here, so it's going to become negative over there. So negative 6K is now equal to 0 minus 12. Negative 6K is therefore equal to negative 12. How do we get rid of this negative 6 now? You divide it. The one that's attached to the letter, you have to divide to get rid of it. Whatever you do on one side, you have to do on the other side. So K is equal to, we have negative 12 over negative 6 gives you a positive 2. So K is equal to 2. And last one before we move on, the determinant of the matrix 6, 2V, negative 5, negative V is 24. Calculate the value of V. So we see they like these determinant questions that's actually algebra. So you need to do the determinant, which is AD minus BC, and then set it equal to what they told you it is. So if they said it was singular, it means it's 0. Now they're telling you the determinant is 24. So AD minus BC, so that's our leading diagonal. That's 6 times negative V minus the other diagonal. So 2V times negative 5. And that's going to be 6 times negative V, so negative 6V minus 2V minus negative 5, so negative 5 times 2 is negative 10V. So negative 6V minus negative 10V, 2 minus signs come together, that's plus, so negative 6V plus 10V. These both have V, so that means this can actually add together. So that's going to be negative 6 plus 10 is 4V. So our determinant is 4V, and we also know that the determinant is 24, so we set those equal to each other. How do we get rid of the 4 that's attached to the V? We divide. Whatever you do on one side, you have to do on the other. V is 6. 24 divided by 4. Okay, finally, the moment we've all been waiting for, solving simultaneous equations using matrix multiplication. So the question over here says, using a matrix method, solve the simultaneous equations, and they gave you the 2 equations. So simultaneous equations will always look like this. They give you 2 equations, and you can use matrix multiplication to solve any simultaneous equation on the exam. So not just in the matrix section. Even if there's a simultaneous equation somewhere else, and this is the only way you understand how to do it, you can do it using your matrices. So step 1, write the simultaneous equations as a matrix equation. So you have to turn this into matrices. So first you're going to make a coefficient matrix. So that means you're going to make a matrix out of all the numbers that are in front of the letters. Those are coefficients. So the number in front of a letter is a coefficient. So you're going to make a matrix using just the numbers that are in front of the letters. So in front of this X we have a 2. In front of this Y you have a 3. In front of this X you have a negative 5. And in front of this Y, if there's nothing, that means there's a 1. So that's our coefficient matrix, a matrix made out of the coefficients of the letters. And then the next matrix is just the letters alone. So you're going to just have an X, Y. This one is always going to look like this. Just X, Y. And then equals, and the answer matrix is just the answers. 5, 13. So you're doing the numbers in front, X, Y, equals the answers. That's step 1. So step 1, you just write the simultaneous equations as a matrix equation. Step 2, find the inverse of the coefficient matrix. So step 2 is going to be to find the inverse of this matrix. So we already know inverse is 1 over determinant times adjoint. So we need to find the determinant of this, and we know determinant is AD minus BC. So in this case it's 2 times 1 minus 3 times negative 5. So that's 2 minus 3 times negative 5 is negative 15. 2 of the same sign together, that's a positive. 2 plus 15, we got 17 as our determinant. And the other thing you need is your adjoint. So remember, adjoint means D and A swap places and B and C change signs. So in this case, leading diagonal is going to swap places. So 1 and 2 swap places. This 3 is going to turn into a negative, and this 5 turns into a positive. Now we can find our inverse. Yes, now we can find our inverse, which is going to be 1 over the determinant, so 1 over 17 times the adjoint. And how do we multiply? By a fraction, we just put everything over the same denominator. So that's going to be 1 over 17, negative 3 over 17, 5 over 17, and 2 over 17. Right? That's the inverse. So that was step 2. So step 1 was write it as, yes. So we've done step 1. We wrote it as a matrix equation. This was step 1. And now we've done step 2. We found our inverse. And the final step is to multiply the inverse times the answer matrix. So what that means is xy, what that means is xy is going to be equal to, you're going to put the inverse that you found first, so it's going to be equal to the inverse, which in this case was 1 over 17, negative 3 over 17, 5 over 17, and 2 over 17, times the answer matrix. So essentially, you're putting the inverse right here and removing the coefficient. This was just to use to make the inverse, and then we're doing the inverse times the answer. That will give us our answer. So we're doing a matrix multiplication, which is right here. So let me write the matrix multiplication that we're doing. So we have the xy is going to be equal to the inverse that we found, which was, everything was over 17. And we had 1, 5, and negative 3, and 2. Right. So we had this and times this. Okay. So continuing where we left off from. So now we just need to multiply this by this. And we know before we multiply, we write our orders. So we have 2 rows here, and then 2 columns, and we have 2 rows here and 1 column. So this tells us yes, these are conformable, it's possible, and our answer is going to be a 2 by 1 matrix. That means our answer is going to have 2 rows and just 1 column. Yes. So our answer is going to look like this. Now let's do some matrix multiplication. So our row 1 should have row 1 things. That's 1 over 17 and negative 3 over 17. And our row 2 should have row 2 things. That's 5 over 17 and 2 over 17. And we only have 1 column, which means that 1 column will have this 1 column things. So that's 5 and 13. 5 and 13. And we are multiplying. And there's an addition in the middle. Now let's just use our calculators for this one. So we've got in brackets 1 over 17 times 5 plus in brackets negative 3 over 17 times 13. And that is negative 2. And our second element is going to be 5 over 17 times 5 plus 2 over 17 times 13, and we got 3. So, all in all, when we multiply these two, we get this. So that means xy equals this. So x is -2 and y is 3. Those are our solutions to our simultaneous equation. And here we just have a note saying matrix multiplication is associative. Why did I make this note here? So we made this note here in case you wanted to leave the matrix, the inverse, as this. So if you wanted to leave the inverse as 1/17 times 1 - 3, 5, 2, and then you multiply the inverse, which is that, times the answer matrix. So you'll have xy is equal to the inverse times the answer matrix. Then you could either do the scalar multiplication first, so you do AB first and then times C, or you could do this times this and then times this. So it's associative. If you're doing 3 multiplications in a row, it doesn't matter if you do A times B first and then times C, or B times C first and then times it by A. You'll get the same answer in the end. So that's just to show that matrix multiplication is associative. So it's not commutative, like the A can't change places, or the B can't change places, or the C. But if they stay in their same order, they can associate either way. So it is associative. We've completed all the objectives for this topic. So let's just do a couple more CXC questions just for the practice, and then we're done. So feel free to try it on your own first, and then press play on the video again to see if you got it right. So first question, find the matrix product right here. So we're going to write our orders first. So we have 2 rows here and 2 columns if we had to draw in some columns. And in here we have 2 rows and 1 column. So in the middle, we notice, yes, this is possible. And our answer matrix will be a 2 by 1 matrix. That means it will have 2 rows, but just 1 column. All right. So let's get straight into it. Row 1 should have row 1 things. That's -1 and 3. And row 2 will have row 2 things. That's a 4 and an H. And we only have 1 column, so everybody in the column should have the column things, which is K and 5. So we need K and 5, K and 5. And we're multiplying with an addition in the center. So what do we get? -1 times K, that's -K, plus 3 times 5 is 15. And down here we have 4 times K, so that's 4K plus 5H. And we cannot simplify these. You cannot add a K and a 15. We cannot add a K and an H. So that's our matrix product. Now, hence, find the values of H and K that satisfy the matrix equation. So this matrix equation says this times this equals 0, 0. And we already found this times this right here. So we can replace this with one matrix. This times this is -K plus 15, 4K plus 5H. And it says it's equal 0, 0. So that means when you do this, you should get 0. So -K plus 15 should equal to 0. If we're solving, you move the thing that's far away from K first. So it becomes -15. So -K equals -15. How do we get rid of this negative? We divide by -1. Whatever you do on one side, you do on the other side. K is 15. The negatives will cancel out. So we found the first one. So we found that K is 15. And now we have to find h. Clearly, we're going to use the second one. So this equals to 0 as well. So it's telling us 4k plus 5h equals 0. Now we already found what k is. So where k is, we can now replace it with 15. So 4 and k is now 15 plus 5h equals 0. So 4 times 15. Let's get our calculators out. So that's 60 plus 5h is 0. We're going to move the thing that's far away from the h first. It's positive, so it's going to become negative. 5h equals 0 minus 60. So 5h equals negative 60. We need to get rid of that 5, so we divide. Whatever you do on one side, you have to do on the other side. And let's put our answer over here. So we have h equals negative 60 over 5. So that means h equals negative 60 divided 5, negative 12. So that's our other answer. Part C. Using a matrix method, solve the simultaneous equation. This. So remember, to solve our simultaneous equations with matrix method, you first have to make the simultaneous equation into a matrix equation. How do you do that? You do the coefficients. So we got 2, we got 3, negative 5, and 1. And then we go xy and equals the answer matrix, that's 5, 13. And I actually think this is the same one we already did. So you can look back to see exactly what happened, but I'm going to go through this very fast. So how do we solve a simultaneous equation using matrix method? You make your matrix equation, so coefficients, x, y, and then the answers. And we find the inverse of this. So to find the inverse, we first need the determinant, which is AD minus BC, which is 2 times 1 minus 3 times negative 5. And if I put that in my calculator, I got 17. We've already been through this. And now adjoint of that same matrix, we just swap the 2 and the 1, change the signs. So that becomes negative, this becomes positive. So our inverse now is going to be 1 over the determinant times the adjoint. With our inverse, what we're going to do now, to find xy, all you have to do is you do the inverse, you put the inverse first, and times it by the answer, 513. So, since matrix multiplication is associative, I'm going to do this multiplication first and then that part. So if we're multiplying this, a 2 by 2 matrix, by a 2 by 1, we know it's possible, and the answer will end up being a 2 by 1 matrix. So I'm just doing this piece first. Then I'll use my fraction after this time, just to show 2 different ways. So first row is going to have a 1 and a negative 3. And the second row is going to have a 5 and a 2. Everybody's in one column, so everybody has to have 5 and 13. And we're multiplying and adding. So this is going to be 1 times 5 plus negative 3 times 13. We got negative 34, and below we have 5 times 5 plus 2 times 13, which is 51. Yes. And so now we found this multiplication. We can do 117 times that, which means you just put 17 over everything. Remember, we're finding xy. All of this is to find xy. Negative 34 over 17 and 51 over 17. You just put everything over the denominator. Let's solve this. So negative 34 divides 17 is negative 2, and 51 divides 17 is 3. So what we found is, I'm running out of space, but what we found is that xy is equal to negative 2, 3. So that means x is negative 2, the top number is x, and y is 3, which if we look back, that was what we found the last time. So it's the same thing. So matrix multiplication is associative. Next question. Determine the value of x for which the matrix 3x 2, 4 is singular. So singular matrix means determinant is 0. How do we find determinant? AD minus BC. So that's 3 times 4 minus x times 2. That is 12 minus 2x. And they said it's singular, so we know 12 minus the determinant equals 0. So we know 12 minus 2x equals 0. The thing that's far away, we move it first. So we got, it's going to become minus, so negative 2x is equal to minus 12. How we get rid of the thing that's attached to the letter, we divide, and so x equals 6. N and P are 2 by 2 matrices such that N is 4, 1, 3, 2 and P is 1, 5, 2, 1. Determine NP. So it's doing NP. So you have to do it in that order. So N first, P next. 1, 5, 2, 1. And they said they're both 2 by 2 matrices, so we already know the orders. They gave them to us. And the answer is also going to be a 2 by 2 matrix. That's 4 elements. And how are we going to multiply? So we're doing row by columns. So row, the first row should have 4, 1, 4, 1. And the second row should have 3, 2, 3, 2. Now the first column should have 1, 2. And let's multiply and add. And the second column should have 5, 1. 5, 1. 5, 1. And now we can solve. So we're gonna get 4 times 1 is 4 plus 1 times 2 is 2. 4 times 5 is 20, 1 times 1 is 1. 3 times 1 is 3 plus 2 times 2 is 4. 3 times 5 is 15 plus 2 times 1 is 2. So our NP is finally equal to 6, 21, 7, 17. That is NP. Given that PN is 19, 11, 11, 4, determine whether matrix multiplication is commutative. So if NP is 621 and 717, but PN is 19, 11, 11, 4. We see that these are not equal to each other. And so, as we know, matrix multiplication is not commutative. All right, there is a part 3 to this question. So, this is just so we can still remember the question. The question was, N and P are 2 by 2 matrices such that N was this and P was this. So the part 3 said, determine N to the negative 1. That is the inverse of N. So determine the inverse of N. And we know inverse is equal to 1 over the determinant times the adjoint. So we first have to find the determinant and find the adjoint. So determinant is AD minus BC, which in this case, the leading diagonal, 4 times 2, minus the other diagonal, 1 times 3. And we got 8 minus 3, so that's 5. Our determinant is 5. We found ingredient number 1. Now we need to find the adjoint, which is to swap A and D, change the signs of B and C. So our adjoint is going to be swap the 4 and the 2 and change these are positive into negatives. That's our adjoint. We found ingredient number 2, so we can put them all together. So it's going to be 1 over the determinant times the adjoint. And to multiply fractions, we know we just put each thing over that same denominator. Negative 1 over 5, negative 3 over 5, and 4 over 5. That is our inverse. Nothing here can simplify it that easily, so we're just going to leave it as that. Next part of the question. Hence, calculate the values of x and y for which, and they have n here. See, n is 4, 1, 3, 2. So 4, 1, 3, 2, xy equals, and then another matrix. This resembles or is identical to the setup for a simultaneous equation question. And how would we solve it if it was a simultaneous equation question? We would know that if this is n, we would know that xy is going to be equal to the inverse of n, the inverse of this matrix, times the answer matrix. So the inverse in front of the answer matrix. Luckily for us, we just found that inverse, so we don't have to do all that work again. So we know now xy is going to be equal to the inverse, which we know, 2 over 5, negative 3 over 5, negative 1 over 5, and 4 over 5, times the answer matrix, which is 1, 2. And how do we do our matrix multiplication? We need to write the orders first. So we know this is a 2 by 2 matrix, and this one is 2 rows, 1 column. So we know it's possible, and our answer matrix is going to be a 2 by 1 matrix. So 1 column, 2 rows. And in the first row, we will have first row things, which is 2 over 5 and negative 1 over 5. And in the second row, we'll have second row things, which is negative 3 over 5 and 4 over 5. And there's only 1 column, so everybody should have 1, 2, 1, then 2, 1, then 2. And we're multiplying and adding. And we're just going to use our calculator for this. So first answer is going to be, let's see, 2 over 5 times 1 plus in this bracket, we have negative 1 over 5 times 2. And that is 0. And our second row, we have negative 3 over 5 times 1. Oh, we forgot the plus. 4 over 5 times 2. So that's 1. So basically, when we multiply these two, we get this. So that means x, y is equal to this. So x is the top, x equals 0, and y equals 1. Yes?